In this video, I will prove that constant functions are the only functions with zero derivative. This will be our first application of the mean value theorem. I had already introduced this problem at the beginning of this sequence of videos. We know that every constant function has derivative 0, but are there others? How do we know these are the only ones? This seems in principle clear, but still needs to be proven, and it's surprisingly not easy to prove. More specifically, here is the theorem I want to prove. I begin with a function f defined on an interval ab, including the endpoints, and I assume the derivative is 0, then I want to conclude is constant. Now, I'm only going to assume the derivative is 0 on the interior, because oftentimes many functions are not differentiable at the endpoints. But in that case, to be able to conclude it's constant everywhere, I need to request yes continuity on the endpoints. So if the derivative is 0, only needed on the interior, but continues everywhere, then the function must be constant. And once again, this is a theorem that seems intuitive, seems obvious, but it isn't. Geometrically it makes sense, but needs to be proven. And the only way we know how to prove this is from the mean value theorem. And now we have the mean value theorem. So let's write down a proof. First, what do I need to prove? I want to show that for every x1 and x2 on the interval ab, f of x1 is equal to f of x2. This is simply the definition of being constant. For every 2 points in the domain, the value of f on them is the same. That's what being constant means. Since this begins with a for all, I'm going to begin my proof by fixing arbitrary values of x1 and x2 in the domain. So I fix them for the rest of the proof, and they are generic, arbitrary. This is the same way we begin any epsilon delta proof for limits. And I'm going to make an assumption for simplicity. I will assume that x1 is less than x2. I can do this because if x1 is equal to x2, there is nothing to prove. And if x2 was the smaller, then the proof would work exactly the same. So whichever is smaller, that's the one I'm calling x1. Now, I want to use the mean value theorem for the function f on the interval x1, x2. Whenever you use the mean value theorem, say for which function and on which interval. And how is it going to help me? I'll need to verify this is okay, but once I verify it's okay, by the mean value theorem, I'll be able to say that there must exist a value of c between x1 and x2 such that the derivative of f at c is this quantity, f of x2 minus f of x1 over x2 minus x1. However, we know the derivative is always 0, so f prime of 0 is also 0, and therefore the numerator must be 0, so f of x1 is equal to f of x2, as we wanted, and we're done. Now, what is missing? Before I use the mean value theorem, I have to verify that's okay. I have to verify the hypotheses of the mean value theorem, which are two. F must be continuous on the closed interval and differentiable on the open. Well, this works. We know f is continuous on the closed interval ab by hypothesis, so it is also continuous on the smaller interval x1, x2, closed. And then we know f is differentiable on the open interval ab because we know the derivative is 0, so it exists, so it's differentiable. And therefore it must also be differentiable on the smaller open interval x1, x2. That's it. So the hypotheses of the mean value theorem are true, so I'm allowed to use it. I'm going to change the next line too, and I'm going to say by the mean value theorem, there exists a value of c such that blah blah blah, and from there continue the proof. And that's it. This is now a complete rigorous proof of the theorem. There are some variations. This is the theorem we just proved. There are a few other versions of this theorem. For example, perhaps we care about proving a function is constant only on an open interval, ab. In that case, we don't need to require anything about the endpoints. We just need to require it to have 0 derivative on the interior, there's nothing else. And we'll be able to conclude it's constant on the open interval. The proof will be very similar to the proof of the previous theorem, and I invite you to see how you have to modify it. It's only a slight modification, and write a proof for this theorem instead. I will finish this video by using this newfound result to solve an exercise. This exercise. I want to prove that there exists a constant c such that this big identity is true. Arctangent of root 1 minus x over 1 plus x equals c minus 1 half arc sine x. And I want to know what the value of the constant is and for which values of x this is true. I invite you to pause the video now and try to solve this problem using the previous result, and then press play and see if I solved it the same way. In principle, this is just a problem in trigonometry. You could just use trig identities to solve it, and that can work. But I think it is faster to just use calculus. And the reason is to prove that this identity is true is the same as proving that this expression is constant. I just send all the parts that contain x to one side, and I want to prove that this is constant. And we know how to do that. To prove a function is constant, all I have to do is check that the derivative is 0. and that is easier. It will take some calculations, but it's easier. So let's do it. Here's my solution. I begin by giving a name to this function and calling it big F. F of x is this expression, and I want to prove it's constant. Let's first figure out what the domain is. This may require some work, so after you do some calculations, you will conclude that the domain is the interval -1 not included to 1 included. Then let's try to calculate the derivative. And if you compute the derivative, this also requires some work, but after doing simplifications, it ends up being exactly 0. But that only works in the interior, from -1 to 1. The function is perfectly well defined at 1, but the derivative isn't, because arcsine is not differentiable at 1. So, already, by the previous theorem, we know that there exists a constancy such that this function is equal to z, but only on the interior. Now the function is also defined at the endpoint 1. And if we take into account that the function is continuous on the full interval, then the function will be constant also all the way to 1. So that's it, I've proven that the function is constant. How do I figure out what the value of the constant is? Probably the easiest way is to evaluate at an easy point, and 0 is probably the easiest value. So the constant must be equal to the value of the function at 0. That's arctangent of 1 plus 1/2 arcsine of 0, and that is pi over 4. So in conclusion, this identity is true for all values of x between -1 not included and 1 included.